Okay. Okay, so let's go ahead and get started. We're going to be, so just as a reminder, you do have a homework that's due tonight at 11, excuse me. Well, first of all, thank you to the 3 people that emailed me saying that I had accidentally put the wrong time on the email that was due last night. I extended it till tonight because I didn't want to give people just a few hours to get it done afterwards. So it'll close tonight at 11:59 p.m. There will be a homework over what we're going over today that is due tomorrow at 11:59 p.m. And then you do have a quiz that's due tonight by 11:59 p.m. Now, for the most part, I scheduled everything so that you didn't have to do anything over the Thanksgiving break, but I will let you know that There is a map commit puzzle that's already available, or actually, I guess it should be available about now. That is due on, I think that's the Monday, no, the Tuesday. I think that's the Tuesday at 11:59 p.m. And I said that because you've already got all the material that you need to complete it even before today's lecture. So if you wanted to do it, so you had one less thing to worry about when you got back, you would have it available. The other thing is a folder will come available. I don't know if it's today, if it's tomorrow. I can't remember how I have it scheduled, but the folder for next week will come available shortly. And I wanted to kind of outline everything that's coming up. So today we're going to work on simple conversions associated with molarity on the Monday after the Thanksgiving break. We will work on, oh dear. Thank you. We will work on the molarity conversions that deal with stoichiometry. And we will also work on that on Wednesday. Of all the things that we do, the molarity dealing with stoichiometry is probably the most difficult, and that's why we're going to definitely spend 2 days working on it. Then the Monday after that week is your 4th exam. It will be over everything, including the molarity calculations, since I will have actually started them on the Monday before that test. So it'll be over everything that we, the rest of the material for this semester. And then the Wednesday after that, I plan to discuss how to study for my exam, which has to do with the blank exams that I also posted and made available starting, again, made them available starting today. So there is one more folder to release after this particular, after the folder that will get released with next week's information. And it basically describes the fact that you have an exam, that there's a review session, and then there's the final exam. So, but otherwise, everything is pretty much released after today or tomorrow. Any questions? Okay, so to get our brains functioning on a Monday afternoon, because I know I'm tired, I imagine most people are tired and are ready for the break. What we're going to start with is we're going to start by doing a couple of calculations related to molarity dilutions, which is the topic we were discussing at the end of Wednesday of last week. So the very first thing I want to point out is I know that these are dilution calculations. And the reason I know that these will be dilution calculations is because we're talking about the same material the entire time. So that's how you're going to know it's a dilution calculation, is because we're talking about the same material the entire time. Now, if it is a dilution calculation, then the equation that you're going to be using is going to be M1V1 equals M2V2. Now, it really doesn't decide, it's not important who is 1 and who is 2, as long as the concentration and volumes that should go together are kept together. So it doesn't matter who you assign as 1 and who you assign as 2, as long as the concentrations and the volumes that go together stay together. So looking at this, we have what volume of 1 molar NaCl. So we could say V1 is equal to a question mark because it went with M1, which was 1.0 molar NaCl. Must be diluted to a volume of 300 milliliters in order to make a solution that is 0.40 molar. Taking our equation and rearranging the equation to solve for the desired variable, our V1 would equal our M2 V2 over M1. Now, before I plug everything into the equation, the only other thing I do is make sure that all my units are matching. Molarity, great. And volume, since one of them is a question mark, it doesn't matter. So our V1 is equal to the 0.40 times 300, all divided by 1.0. So V1 comes out to be 75, I think. No, wrong. Comes out to be 120. And that would be in milliliters because that was the unit of our volume to begin with. Now, the next problem is also a dilution calculation. We know that it is a dilution calculation because our starting material and our ending material are identical. So since it is a dilution calculation, we will again use M1V1 equals M2V2. We only use M1V1 equals M2V2 for dilutions. So we need to make a 10-liter solution of 1.2 molar. KNO3. What molarity would the KNO3 solution need to be if you use 2.5 milliliters in the process? I mean, 2.5 liters. Rearranging this equation to solve for our desired variable, that's M1 V1 over V2 is equal to M2. .0 liters times 1.2 molar, all divided by a volume of 2.5 liters will give us our new molarity, and that new molarity comes out to be 4.8 molar. KNO3. That is all there really is to dilution calculations. The hardest part is recognizing it so you know which equation to use. And then making all of your units match so that your volume is the same volume unit and your molarity is the same concentration unit. So with respect to molarity, we have now talked about two things associated with molarity. The very first one was just the formation of a solution from a solid, where we would take grams of a substance and we would make a solution by dissolving that grams into a volume of water. The second one was a dilution calculation, where we started with a liquid and we made a liquid that was more dilute. Now, what we get into is the beginning of conversions. With molarity as the conversion unit. Now, folks, one of the skills that most people want to fly over and ignore
is when you see the symbol for molarity, which is the capital M, take a minute, actually it's a few seconds, and rewrite that concentration into its subunits, which is moles over liters. So if I have 16 molar H2SO4, what that means is I have 16 moles H2SO4 over 1 liter of solution. Or like in that sodium chloride, the 0.4 molar, it would mean I have 0.4 moles of NaCl per 1 liter of solution. Now you may ask why? Why take that time to take that capital M and rewrite it into its subunits? And I'll tell you what my experience is from grading a gazillion papers over the time I've been teaching. Not quite, but it feels like it some days. I have seen students take that capital M and mistake it as moles when they start doing their calculations. I have seen students take that capital M and not know what to do with it when it got to the calculations. But if you take the time to take that capital M and rewrite that concentration into its subunits, what you should be able to see is that this looks like a conversion factor. Because all of your conversion factors we've talked about from the beginning have been fractions. This is a conversion factor. It is a conversion factor that allows you to go from an amount of material into its volume. And the key here, folks, when we start talking about these, is that whole volume issue. Anytime I see a volume unit, and I start talking about stoichiometry or conversions, I'm going, molarity is my conversion factor. See a volume unit, molarity is going to be your conversion factor. Now, whether you leave the molarity as moles over liters, or you flip it to be like 1 liter over 16 moles of sulfuric acid, that, folks, that is determined by what you need to get rid of in your conversion. If you need to get rid of liters in the conversion, then the original format will be your format that you need. But if you need to get rid of moles in your conversion, then you need to flip it. Now notice once I flipped this conversion factor, I literally did the entire thing as a flip. The 16 moles stayed as 16 moles, whether it's in the numerator or whether it's in the denominator. I flipped the entire thing over. So what we're going to do now is we're going to look at some conversions. Okay. How many moles of NaCl are present in 600 milliliters of a 1.55 molar NaCl solution? Okay, what have I been given? I have been given 600 milliliters of solution. And I have been told that that solution is 1.55 molar NaCl. I see that capital M and I go ahead and rewrite it. That's 1.55 moles of NaCl per 1 liter of solution. Doing so helps you to determine the fact that it is the volume that you actually need to convert into moles NaCl. And the reason we're going to start our conversion with the volume unit is because there's only one unit there. For all calculations, folks, when you can start with a number that has a single unit associated with it, that is your best bet. So that is why I will start with the 600 milliliters, because it actually has a single unit associated with it. Now, we can play this whole idea like we've been doing, where we go in and go, okay, I have the same substance, so that's fine, but I have volume. So volume tells me that I'm going to need the molarity. Anytime I have volume, it tells me I want, come on, be nice. Anytime I have a volume, it's telling you that the molarity is the conversion factor. Now, to be able to use this volume conversion factor, I notice that I need the volume in liters. So I'm also going to need a second conversion factor. I am going to need a metric prefix conversion factor. And that is 1,000 milliliters is equal to 1 liter. Or you can use 1 milliliter is equal to 1 times 10 to the minus 3 liters. Either one. Okay, so now I've used everything I have to do this. So I'm ready to start this problem. We'll start with the 600 milliliters of solution. We'll use the metric prefix system to convert that into liters of solution. The milliliter of the metric prefix system went into the denominator so that the unit and the substance would cancel, leaving you liters of solution. Now you use your molarity. 1.55 moles of NaCl will go in the numerator, while the 1 liter of solution goes in the denominator. The liter had to go in the denominator in this case so that the unit and the substance would cancel, and you're left with moles of NaCl. And that comes out to be 0.93 moles of NaCl. Let's look at another one. What volume of a 0.25 molar calcium hydroxide solution can be made using 0.55 moles calcium hydroxide. Making a list of information I was given the 0.55 moles of calcium hydroxide. I was also given 0.25 molar calcium hydroxide solution. I take a moment with that molarity and I rewrite it. That is 0.25 moles of calcium hydroxide per 1 liter of solution. By rewriting the molarity, you will see that it contains 2 units. That is not what the one I want to begin with. I want to start with the moles of calcium hydroxide because there's only a single unit associated with it. So we're going to take that moles of calcium hydroxide and we're going to convert it into volume. Now it didn't specify, so you could use liters. If it specifies, then you've got to convert it to the appropriate volume unit. But if it doesn't specify, liters is fine. So I look over this thing and I see, okay, we're dealing with one substance. We start with moles and we go to volume. So the molarity is going to be our conversion factor. Because I see this volume unit, so I automatically know I'm going to need molarity as the conversion factor. So we start with our 0.55 moles of calcium hydroxide. Now, I got to get rid of moles of calcium hydroxide. This is where you can invert your molarity, because by inverting the molarity, the 0.25 moles of calcium hydroxide can go in the denominator, while the 1 liter of solution goes into the numerator. We place the moles in the denominator so that they would cancel. That's the reason we inverted it. And now we're ready to do the math because we have liters of solution, which comes out to be 2.2 liters of solution. Questions? Let's look at another example. How many grams of calcium hydroxide are needed to produce 500 milliliters of 1.66 molar calcium hydroxide solution? Reviewing what I have been given, I have 500 milliliters of solution. I know that the solution is 1.66 molar calcium hydroxide. Rewriting that molarity, that means it's 1.66 moles of calcium hydroxide per 1 liter of solution. By rewriting the molarity, you will see that the molarity consists of 2 units. That's not the preferable place to start. Instead, I'm going to start with the item that has only a single unit attached to it, which is the milliliters of solution. So it is the milliliters of solution that I will be converting into grams of calcium hydroxide. Now, tearing this thing apart. First thing I see, okay, I have a volume. Volume means that my conversion factor is molarity. Now, I notice though that with my molarity, I'm dealing with liters, whereas I'm starting with milliliters. So that means I'm going to need the metric prefix conversion factor as well, where 1,000 milliliters is equal to 1 liter. The other thing I note is that I am dealing with grams. And just like before, this is the same as before. When I see grams, I know I need molar mass. So I need the molar mass of the calcium hydroxide. Calcium has a mass of 40.078. Plus I have 2 oxygens at 15.9994 each. Plus I have 2 hydrogens at 1.00794 each. So I have a mass of 74.09268 grams calcium hydroxide is equal to 1 mole of calcium hydroxide. Oops. Okay, so we're ready to begin this calculation. We'll start with the 500 milliliters of solution. We'll use our metric prefix conversion factor to get that from milliliters of solution into liters of solution. With the metric prefix conversion factor, the milliliters had to go in the denominator so that they would cancel. We now have liters of solution. Now we can use the molarity we were given. In this particular case, we want to keep it as is because we needed the moles of calcium or we needed the liters of calcium hydroxide solution in the denominator so that the liters would cancel out. Leaving you moles of calcium hydroxide, and now you can use your molar mass of calcium hydroxide to convert that into mass. The moles had to go in the denominator so that the unit and the substance would cancel out, and we were left with grams. Keying that into the calculator, you get 61.5 grams of calcium hydroxide. My tablet is being not so nice. There we go. Questions? Okay, let's look at another, or let me give you one to work on. What volume of a 0.88 molar solution can be made using 130 grams of iron 2 chloride? Okay, let's see how it's going. So first of all, I listed out what I had. I had 130 grams of FeCl2. I also knew that the concentration of the solution I wanted was 0.88 molar. I took that molarity and broke it apart so that I could definitively say I wanted to start with the grams of FeCl2 since that value had only a single unit associated with it. So we're going to take that 130 grams of FeCl2 and we're going to turn it into volume of solution. Now, as soon as I saw the grams, that told me I was going to need my molar mass as conversion factor. And as soon as I saw the volume, it told me that I was going to need the molarity as conversion factor. So then you take the 130 grams of FeCl2, and the first thing we're going to use is the molar mass of FeCl2 in order to convert that into moles of FeCl2. So the 126.745 grams of FeCl2 will go into the denominator, with the 1 mole of FeCl2 going into the numerator. The grams of FeCl2 went into the denominator so that the unit and the substance canceled, leaving moles of FeCl2. Now we can use our molarity, but in order to use this molarity, we are going to need to flip it over so that the moles are in the denominator. So the 0.88 moles of FeCl2 will need to go into the denominator, with the 1 liter of solution going into the numerator. The reason that we had to flip it over is so that the unit and the substance of moles of FeCl2 would cancel, and that left liters of solution. So keying this into the calculator, we have 130 divided by 126.745 divided by 0.88. And you get out the 1.17 molar FeCl2 solution. I'm sorry, liters of FeCl2 solution. Need to pay attention to my own units. That's 1.17 liters of FeCl2 solution. Questions? One of the things that makes this type of problem challenging is that if you look at the last 4 examples, none of them are the same. There isn't an immediate pattern necessarily with molarity, like there is some of the other calculations that we've done. That's what makes molarity a bit more challenging. And that is why it's important to be able to recognize what conversion factor you need when, because you can't simply memorize it. It is something that you have to just practice doing and realize when you use what. And the only way to do that is to really learn how to pick things apart like we've been doing. Okay, I'm going to give one more example and then we will probably call it a day. How many milliliters of solution are needed to make a 1.66 molar solution that contains 112 grams of KMNO4. Okay, so let's look at this problem. First thing you do is figure out you've got 112 grams of KMNO4 and 1.66 molar solution. By breaking the molarity down into its subunits, you find you've got 1.66 moles of KMNO4 per 1 liter of solution. By breaking the molarity down, it is obvious that you should start with the grams of KMNO4 to convert that into milliliters. Breaking this thing, breaking what we have and what we want to solve for, the first thing I notice is I have grams, so I'm going to want to use the molar mass. The next thing I notice is that I have volume. So that tells me that I'm going to need the molarity, but more specifically in this particular case, I'm going to need the metric prefix system because of the fact that that volume is needed in milliliters. So getting ready to do this problem, you have 112 grams of KMNO4. You start with the molar mass of KMNO4. The gram portion of the molar mass goes into the denominator with the volume portion, with the mole portion in the numerator. We do that so that our unit and substance cancels out, leaving moles KMNO4. We then use the molarity of KMNO4 to get it And in this particular case, we are going to have to flip the KMNO4 over because we need to get rid of moles. So the 1.66 moles of KMNO4 will go into the denominator with the 1 liter of solution into the numerator. We had to flip it again so that the moles would cancel out, leaving us liters of solution. And then you can use your 1,000 milliliters is equal to 1 liter in order to convert it into milliliters. And when you complete this calculation, you get an answer of 427 milliliters of solution. Questions? We will start with the problem just to get our conversions going on Monday after Thanksgiving break. And after that, we will get into conversions using stoichiometry. Yes. Otherwise, I will see you after the Thanksgiving break. Our Thanksgiving break is Wednesday, Thursday, Friday. It's okay. Trust me, I've had to remind myself a few times that I don't have class on Wednesday.